What's up guys, welcome to another video. Today we will be explaining Einstein's theory of relativity in 3 different ways. We will be discussing movement and how it relates to traveling through spacetime. The 3 explanations will be laid out from most simple to least simple. Feel free to pause or rewind the video to easier understand the concept. First, we need to set some ground rules. Throughout the video, I'll be using c as the speed of light as used in Albert Einstein's famous E=mc² equation. It is also recommended that you have a basic understanding of algebra. Also, this is a spaceship, because I'm lazy. Before we get to the first explanation, I need to explain something first. Let's say that you and me are on opposite sides of a bus. The bus is going straight east 50 miles per hour on the equator. Let's also say that we are throwing the ball to each other and can throw it at 10 miles per hour. If you are throwing the ball to me, then we both perceive it to be going 10 miles per hour. However, if a person outside the bus was watching, they will perceive the ball to be going 40 miles per hour because of the speed of the bus minus the speed of the ball. But if I were to throw the ball to you, we would perceive the ball to be going 10 miles per hour, while the person outside the bus would perceive it to be going 60 miles per hour because of the speed of the bus plus the speed of the ball. If somebody in a spaceship watched me throw the ball to you from space, then they would perceive the ball to be going 1,060 miles per hour because of the speed of the ball plus the speed of the car plus the speed of the Earth's spin at the equator. This is the concept that movement is relative to the things around you. Relative to the bus, the ball is going 10 miles per hour. Relative to Earth, it is going 60 miles per hour. Relative to a stationary position in outer space, it is going 1,060 miles per hour. What if the bus turned on its headlights? Would the light be going the speed of light plus 50 miles per hour? No. Everyone, no matter their position or trajectory, perceives light to be going exactly the speed of light. With that, we can head to the first most simple explanation. Explanation number 1. Clock tower. Let's say that you are in a spaceship at the foot of a clock tower. Your spaceship can and will go half the speed of light. When the clock tower says exactly noon, you accelerate away from the clock tower. After a minute has passed, the people at the clock tower say that it's 12:01. But you look back at the clock tower, and light from when the clock tower said 12 and 30 seconds is hitting your eyes. Now let's say that your spaceship can and will go exactly the speed of light. When you accelerate after the clock says noon, a minute passes, and the people at the clock tower say that's 12:01. But you look at the clock tower, and light from when it said noon is still hitting your eyes. Now let's say that your spaceship can and will go exactly twice the speed of light. When you accelerate after the clock tower says noon, a minute passes, and the people at the clock tower say that's 12:01. But you look at the clock tower, and light from when it said 11:59 is still hitting your eyes. Keep in mind that this is a very simple way of explaining the theory of relativity. Let's move on to the next explanation. Explanation number 2. Photon clock. A photon clock is basically light bouncing in between 2 mirrors. When the light bounces in between the mirrors a certain amount of times, a second has passed. Let's say that you strapped one of these to the back of your spaceship, and while I was watching, accelerated into space. The zigzag is the way that I would see the light bounce off the mirrors. However, since light is going the same speed for everyone, you would look back and see this. The light is going straight up and down. For me, I see less bounces of light than you do, so you travel faster through time than I do. Let's start on our last explanation. Explanation number 3. Ned, Ted, Fred, and Joe. This is a grid, and on the top you can see certain segments that are numbered 1 through 8. Let's pretend each one is a light second long. A light second is the distance light can travel in a second. Let's say that Ned, Ted, Fred, and Joe are going to race each other, and whoever is the furthest after 4 seconds wins. Ned's spaceship will go 0 times the speed of light, so he will remain stationary. Ted will go half the speed of light. Fred will go exactly the speed of light, and Joe will go twice the speed of light. I'm going to count down from 5 to start the race. 5, 4, what's that? A spaceship that looks just like Joe's has arrived at the 8-second mark. Continue the race as planned. 3, 2, 1, go. Let's look at Fred's spaceship first. When the race started, Fred accelerated forward at the speed of light. So after 4 seconds, he was at the 4 light second mark. Now let's look at Ted. The moment the race started, he flew into space at half the speed of light. So after 4 seconds, he was at the 2 light second mark. Ned's spaceship didn't move at all, so he stayed at the 0 light second mark. When the race started, Joe's spaceship flung to the 8 second mark. Nothing too crazy, right? Well, let's say that the moment the race started, all the racers turned on their headlights. It would look something like this after 4 seconds. When Ned looks in front of him, he sees 1, 2, 3, 4 light seconds worth of light in front of him. He also perceives 4 seconds. Ted sees 1, 2 light seconds in front of him. Because everybody perceives light to be going the same speed, Ted thinks the light has only been traveling for 2 seconds, and therefore only perceives 2 seconds. To Fred, the light hasn't been traveled at all in front of him, so he perceives that no time has passed. This is where it gets weird. Joe sees 1, 2, 3, 4 light seconds behind him. Theoretically, this means Joe has experienced negative 4 seconds and traveled to the 8 light second mark 4 seconds before the race even started. No one has the slightest idea what Joe experienced on that ship, but at least he won the race. Why do we not feel time slowing down for us when we move? As discussed earlier with the bus analogy, movement is relative to the things around you. So if you are moving, you don't notice you are moving through time because everything around you that is going the same speed is moving through time at the same rate. So if you and me were on a moving bus, time is not speeding up relative to the bus. Why don't others notice you time travel when you move? When you are moving on a bus going 50 miles per hour, the change in time is so minute, see what I did there, that it is for the most part unnoticeable to the naked eye. However, there have been a few instances otherwise, such as clocks in space stations and satellites that are sent back to Earth have been found to be around 2 minutes late per year they were up there. This is because the space stations go a lot faster than people on Earth do. TLDR. Time and movement are relative to the things around you. If you're on a moving bus, you perceive things inside the bus to not be moving even though they are. The faster something moves, the faster it moves through time until it hits light speed. Going any faster would theoretically bring you to the past. Time is a variable, fluctuating, confusing part of the cosmos that is only what we perceive it to be. I hope this video helped you understand the theory of relativity. Make sure to like, subscribe, and turn on those post notifications to be a citizen of Llama Town.